used, right? So means how it is done there, that I wanted to ask.
Yeah, so the assume that the spectral density of noise remains the same, okay? That is increased or decreased based on the amplification, okay? And the filtering reduces the total noise because it's an integral across the bandwidth. So if you cut down, if you attenuate contribution from other frequencies than what you want, which you selection that you do in your filter, effectively, yes, there will be reduced noise fluctuation, but still the spectral density within the band is of interest is constant.
Okay.
Same as the previous one, unless there is amplification.
Okay. Yeah.
Or attenuation due to the filter.
Yes.
Any other question?
So these will be shared, right? Your slides?
Yes, I can do that if you think it's useful.
Yes, sir. I would like to go through them once again because like sometimes you lose.
Okay, yeah. I can understand. There was lots of disruption also, so the continuity was lost on many occasions. So.
Thank you, sir.
Yeah, I would make them available. Probably later in the day, I will just get rid of unwanted slides and give you, so that it will be less confusing.
Sure, sir. Thank you.
Yeah, we are also planning to edit the videos and put them up, but that may take a little while.
Right. Any other question? I think Akshay's hand is still raised. Probably he might want to lower it. Probably raised for some other reason earlier. Okay. I will just check if there are any questions in the window. No, I see none. All right. Should we proceed to the Fourier transforms then?
Yes, sir.
All right. Let me share the screen. Okay, can you see the screen now?
Yes, sir. It's visible.
Go to the, all right, we have a slideshow. Right. Okay. So how many of you are already familiar with Fourier analysis? Can I have a raise of hands? Okay. 1, 2. Okay, pretty large number. That's good to know. All right. So of course we have lots of people potentially that can help their colleagues to also get equally familiarized with the Fourier transforms. This is one of the most used transforms in all fields, I might say. So we will introduce or refresh for people who are already familiar the Fourier transforms. And so among the various great things that Fourier did, these transforms named after him have really enriched and literally transformed many academic lives and will continue to. And so this tool is very empowering, to say the least. If you are going to be in research, do familiarize yourself and get to even love them as you go along. And you will see why I use the word love them, because ability to see a distribution and visualize its Fourier domain description gives you a chance to get much greater insight, and you can relate that to physical context much more easily. And that's an advantage one should not lose. All right. So the basic idea is given any function which is finite, you can think of it as a grand superposition of sinusoids of various periods of oscillation, each scaled and phase shifted appropriately to collectively match the function. So you can think of it as a procedure where you are trying to find the best fit by using basis functions or component functions as sinusoids. I'm sure some of you might have even done fits using polynomials to any given curve or some function at hand. And what you're doing here, instead of using polynomials, you're using a specific set of oscillating functions to do that. And it can be shown that every finite function has, for every finite function, there exists a Fourier description. So similar to many linear transforms, we have Fourier transform as also a strictly linear transform, where the basis functions are sinusoids. And by sinusoids, I mean cosines and sine functions. Okay. So I think, okay, this part is same as what I've said. All right. Have I repeated? Somehow something has got repeated here. So these are, you can think of them as complex scale factors, where instead of thinking of real sine and cosine functions, you can think of them as, e to the power, the argument which contains product of time and frequency, or some other pair of coordinates which form the pair, which could be a spatial coordinate or angular coordinate in the context that we had just looked at in the previous lecture. And so when you get this fit with a large number of sinusoids with its amplitudes for sine and cosine, you can combine the two if they are at the same frequency and define a complex scale factor which will have a magnitude and a phase. So you can combine these in a form that where you list them in order of increasing frequency, these scale factors. That is essentially the Fourier transform description of a given function. So one of the important properties to remember is, or in this transforms, is them being linear. What it means is sum of two functions will have a Fourier transform, which is sum of their respective Fourier transforms and things like that. Also importantly, one should note that there is no change of information content across these domains. When you go from one domain to the other domain, nothing is lost. It's like a perfect translation of a paragraph. And you can always translate it back and you will get the original. In cases where there is nonlinear transforms, you will find that some mixing would have happened, and that mixing cannot be uniquely undone, which might make it harder. So one of the properties of both reversibility and the information content not being changed is related to the linear nature of the transforms. So and there is uniqueness about this representation. That means there is a single representation, that there are no multiple possibilities, that multiple descriptions you will get. And so it's at the same time, you should remember that every point in one domain is not mapped to the other corresponding point in the other domain. There is no one-to-one mapping like this. Information of the entire span is combined in certain way to produce a point in the other domain. So there is no one-to-one mapping, except the combination is such that when combined in a certain fashion, all those points will produce the information at any given one point in the other domain. Now, the uniqueness is ensured by the fact that the basis functions we use, which are the sinusoidal functions, are mutually orthogonal in nature. What does that mean? That there is no correlation of one basis function with another basis function. It also means that one basis function cannot be produced by any combination of any linear combination of all the rest of the functions. So when something has to be represented by a particular sinusoid, it can be represented by only that sinusoid. Nobody else conspiring can mimic the contribution that a particular sinusoid makes. So that is what makes the representation unique. As I said, in Fourier transform, the basis functions are sinusoids. Net correlation between any two sinusoids of different frequencies is strictly zero, integrated over wide enough span, ideally, strictly speaking, from -infinity to +infinity in whatever domain in which the function is given. So this is true even between cos and sine. If you know, they are shifted versions of each other by 90 degrees. And formal correlation, if you compute by cosine and sine, you get another sinusoid, which, when integrated because of the oscillation around, symmetric oscillation around zero, you will get zero. All right. What else the basis function set should ensure? That while they are independent of each other, that's very nice. They should also be sufficient to describe, the set should be sufficient to describe any finite function through the linear superposition of these basis functions. So in other words, the basis function should be mutually exclusive and collectively exhaustive of all possibilities of finite functions. Okay. So, and sinusoids as basis functions indeed satisfy this requirement. This is the formal definition, which you must have seen in a variety of places, or whenever you click on Google on this, you will get this. So what is here is the Fourier transform of this function f of x, okay, which will give you the conjugate coordinate representation in the conjugate coordinate called S here. And if that is so, then the contribution at S in the Fourier domain of the function fx can be computed by multiplying it by e to the power minus I times I being square root of -1 times x times s integrated over the range of x. What is this really representing? fx, as we said, is a superposition of large number of sinusoids. When you take this large number of sinusoids and consider this as a sum, and then multiply this by something which has also oscillatory nature, you will find that you can think of this being a multiplication with each one of the terms that sums together to produce f of x. So, excuse me. Sorry, I had to put the phone away. All right, so where I was, okay, so if f of x is a sum of superposition of linear superposition of large number of sinusoids, each one of them is represented as some amplitude, okay, times e to the power I times x times s, right? And the s being different, okay, you will find that the product corresponding to the same s will only survive. All others will not survive because of mutual orthogonality, okay? And this is how you will filter out the amplitude, and if there is any phase difference between the representation of that particular sinusoid in the summation of such sinusoids giving rise to this f of x, only that term will filter out. And this is the basis of extracting the information about the amplitude and phase of the component at s given the function f of x. The inverse transform is just everything else being same, reversal of the functions and change of sign of this. And if you make any mistake here in signs, you will just see that you can substitute s by minus s or x by minus x and cause flip of the axis. You will get a image picture of sidewise flipped picture. All right. So there are representations you will find which might differ in the way these things are normalized. Ideally, the representations which make sure that there is a certain physical picture which is maintained are more preferred. So you will find that a form, as long as you have made sure that the normalization factors are arranged in such a way that when you transform it back through a loop, that means take a function, take its Fourier transform and back, you should get back the same function. And you will find typically the factor in practice that is acquired in discrete transforms is the number of points. So either you can divide that by number of points at appropriate time in the forward transform or in the inverse transform, or some people prefer to do that in parts where they divide by square root of n in each one of the transforms. All right, this is sort of not the discrete version, so that's why this 2 pi appears, but in principle there will be a factor commensurate with that. Okay. So the integral of the condition for Fourier transform to exist, that the integral of modulus of the function integrated from minus infinity to plus infinity exists, and that any discontinuities one might have in the function are finite. Okay, so the appeals of Fourier transform are plenty. These are, there are many important Fourier pairs relevant to optics, as we ourselves have seen, which relate to the description. For example, the Young double slit experiment you will find that the aperture distribution, which can be thought of as two boxy functions, is what describes Fourier transform of which describes actually the fringe pattern. How is it? You will find, imagine if you were to have very narrow slits, it will appear like two delta functions, and those two delta functions with respect to some Fourier point at the center can be thought of as two frequency components symmetrically placed, which will correspond to a cosinusoid function. And because you have finite width, you will have the Fourier transform of that, which is a sinc function, and so you will get a product of sinc function with cosinusoid, and that's what will describe the fringe pattern associated with the two finite slits separated by some distance. We have routine relevance of this in general astronomy, instrumentation and signal processing. Efficient computations can be made possible by use of Fourier transforms, particularly convolution in large data sets and correlations. They can be effectively performed as multiplications primarily by going to the other domain. You can also correspondingly do integrations and differentiations, which translate to multiplication by coordinate value or division by the axis value. So those are details which we may or may not go into details about integration and differentiation, but certainly we'll look at convolutions and correlations in somewhat greater detail. It also makes it possible that measurements can be made in any of the domains, and hence one can opt for a feasible domain in which measurements are possible. And this is the classic example of that in the context that we are presently discussing is the synthesis imaging. I generally call it in the lighter vein that there is a saying in Hindi that जब सीधी उंगली से घी नहीं निकलता है उंगली टेढ़ी करनी पड़ती है. So the टेढ़ी उंगली is the Fourier domain solution where it's difficult to make a big telescope and make measurements of the sky in the directions of interest. You go to its Fourier domain where you can patiently measure the pairwise correlations and fill the information in its Fourier domain and then transform it back. So it's also useful in, as I said, when you can visualize or view the function and its Fourier description, you will get to know several things that won't become obvious just by looking at the function directly. Particularly if you want to see certain effects of certain processing or certain operations done in one domain, they might be easily visualizable in the other domain. And most importantly, that in each one of the domains, the function might have different spreads. You might have a function, for example, a simple sinusoid, which is, going from one end to the other of the span that you might be looking at. There might be superposition of certain sinusoids, and then it will be very difficult to make out, even there are a finite number of them. It will be difficult to make out what exactly is contributing. Whereas when you go to the Fourier domain, you will get that described in a more compact fashion. Maybe such as a countable number of sinusoids which are contributing to this thing, and you can easily decipher what's going on. One of the direct implications of this aspect is that energies are conserved in both the domains as much as the information is also conserved. And so imagine that there is certain phenomena that you're looking at, whose pattern you're looking at in one domain. If in the other domain it has more compact description, you will find that it occupies a smaller range of the parameter space in the other domain. You will find that energy conservation will imply that the contribution there will be much taller, right? Because it's after all integral of the square of the function is what the energy is, and you need to know the domains. So if it's confined to a narrow parameter range in the other domain, you will find the function will be taller, and the contrast of that with other contaminants, noise, anything randomly varying will be highest possible. So this is another way of detecting things which are otherwise difficult to see. And another similar classic simple example is if there is a large amount of noise and a tiny sinusoid is buried in it, it's very difficult for you to make out or even assert that there is something like that. But when you Fourier transform, you might find all the energy on the sinusoidal pattern is concentrated in one point or very compact region, whereas the noise is equally distributed, being of random nature, still keeping the energy same in both the domains. And you will find that the contrast has improved, and there is no doubt about the presence of such a sinusoid if it indeed does exist. Hopping from one domain to another domain is not very difficult. Once you get tuned to the thinking, it's real fun and empowering too. So I would encourage people to actually go deeper into this as we go along and try to visualize things rather than sitting and computing Fourier transforms, which you of course will do in the cases that are required, but the elementary picture can emerge rather quickly from basic considerations. And for that, we need to know how things translate from one domain to another domain. I will not go into details of this. I will share these transparencies, and you can also find out these other details because I will be now compressing 4 sessions into 2. So I'm going to gloss over some of these. So there are certain properties of odd and even functions that we can exploit because of the Fourier translation for them is specific. We know that any function can be written as sum of odd and even function by just doing this operation. The Fourier transform of an odd and even function are specific. For example, for an even function, the Fourier transform is always real. For an odd function, it's always imaginary. I mean, only the imaginary component is non-zero. And so you can, if you have a function and you can imagine them to be, combination of it, then you can visualize their Fourier transforms also with equal ease. Okay, so you can go through this list of how this translates into various combinations of when the function is of certain nature, how the transforms will be, and so on and so forth. The one that we will be using most of the time is real and asymmetric, where our sky brightness distribution, intensity distribution is real, and there is no particular symmetry associated with it. And that leads to its Fourier domain description, which is complex and Hermitian. So there's a Hermitian symmetry. What does that mean? That the points corresponding to the negative frequencies are simply complex conjugate of what is on one side of the origin. So this is something that helps us greatly in the context of the interferometers that we were talking about, where the visibility that we measure is a result of the Fourier transform or represented in the Fourier transform of the sky brightness distribution, which is real and asymmetric. And so the visibilities will be complex and will have Hermitian symmetry. And that makes life easy, because if you measure it at one frequency, you know it's one special frequency, you know its value at the frequency with the negative sign on the other side, diametrically opposite point. And this makes life easy, because you need to measure it only on one side. The other side measurement is practically done, and you will put the complex conjugate of your measurement of visibility at the diametrically opposite point. Okay, this is just the same representation pictorially. I'm going to skip over that. I'm also going to skip over this. These are some examples of how you keep on adding sinusoids and you get functions associated with the superposition. This is something that you can already visualize very easily, and for people who already know about Fourier transforms, this might be redundant, but it's good to sketch things yourselves and see how things will appear. Or whenever you look at a function, try to imagine what this could be superposition of, if it happens to be a simple enough function to visualize. Simplest of the functions, like square wave, you know that if they are superpositions of sinusoids which are harmonically related. And so you can see how that develops into a very boxy, like sharp transition features. You will find that the higher and higher harmonics make that possible. With the fundamental, you get only a very smooth description. When you begin to add its harmonics, you begin to sharpen these transitions. Okay, there are some transforms which are easy to note and remember, or easy to have on your fingertips, and I will mention those. This is the famous Gaussian function. A Gaussian function transforms to another Gaussian in the other domain. A sinc function is a Fourier transform, has a Fourier transform of a rectangular window function, or vice versa. Remember that whatever is on the left and right, I could have easily flipped it, and the same thing will hold good. A sinc square function has a triangular function as a Fourier transform. A function which is constant across one domain is represented by a delta function. A function which has two delta functions is a cosine function. The two delta function with 180-degree phase shift will make a sine function. Okay. Now, this is something that I stressed even talking about it earlier. There is the uncertainty principle, which is at the heart of everything, particularly across these Fourier pairs. You will find you have certain span of the function in one domain, or certain feature of certain width in one domain. It will ensure coherence over inverse of that width, after which the coherence may not exist. So you will find that a narrow feature in one domain leads to coherence over larger scale in the other domain. So you will find the products of the widths typically is conserved. And that's tied up with the uncertainty relation, much the way delta x, delta p is, in the best case, it's cannot be smaller than something. So, so this is the same statement, measurements of Vt on time scales delta t, which is less than inverse of the bandwidth, are correlated, and so they are not independent. And this comes in handy where when you use a certain bandwidth, you don't have to go finer than time scales of inverse of the bandwidth, because nothing is changing during that time. This is also relevant to the way you sample your data in discrete representations and related to Nyquist criteria and so on and so forth. All right. Now let's look at some of the theorems and properties of Fourier transforms. We have, if you take the function, we have seen the linearity properties already, may not have described them, but all that it means is, I think some of them are here as well. So let me not jump this stage. So if you scale one of the axes, suppose f is a function of x, and if you want to know f of ax, what Fourier transform that will have. So if f of x has a Fourier transform of f of s, then you can easily write the appropriately scaled version. So if you expand an axis, the description in the other domain shrinks by the same factor. And of course, this is a normalization to make sure that the energies are conserved. If you simply add two functions whose Fourier transforms you know separately, you can, without having to compute the Fourier transform of the combination, you can write them as a combination of the Fourier transforms. There is a shift theorem where people who are familiar with their algebra will know that simple change of variables can be performed to get the change that would occur in the Fourier transform. So if f of x function is shifted by an amount a along the x-axis, you will find that the Fourier transform of that is the original Fourier transform times a phase gradient. And the phase gradient is proportional to, it's a linear phase gradient, and it's proportional to the amount of shift. And this is what comes in the a variety of ways. If you shift a function in time, you will find its spectrum will now have additional phase gradient, okay, compared to what it had, what description it had earlier. If you have a wavefront coming from certain angle, you will find, if you already have some description across the spatial coordinate, right, and the wavefront was arriving from vertical, you will find the equiphase surface is exactly the way it should be for the wavefront. But if the wavefront is coming from an angle which is away from the vertical, you will find it's like a shift in angle. And the shift in angle will cause a phase gradient along a spatial coordinate, which is its Fourier counterpart. And so you will find along across the space, if you measure at any instant the phase of that wavefront, you will find it's differing by in a linear way as a function of the distance from some reference point and proportional to the angular shift that you have given. So this is very handy in a variety of ways to remember. And this is exactly at the heart of the shift of the delta functions. For example, in this you knew that a single delta function at 0 will have constancy of value in the other domain. What you have done is you've shifted this function on one side once and the other side once. And then you have seen that this caused a phase gradient because of this shift, and another phase gradient of opposite sign in the other way. So you landed up adding e to the power something with e to the power minus something. And that's what led to the cosine function. All right. When you multiply two functions, this is a particular case of a modulation where a sinusoid is multiplied with this function. You will find that you will have the replica of Fourier transform of this function, which is capital F of S, located at the locations of the components of the cosine function. The cosine function itself is represented by two delta functions. And so you will find the replicas of that are created at the two locations. So that's what happens if you modulate the signal with fx. If you perform convolution of two functions, you can show that the Fourier transforms of the component functions that you convolved will be simply multiplied. A corollary of that is if you take autocorrelation function, which is represented as f of x times convolved with f star of minus x, you can work it out and show that the Fourier transform will be modulus square of the original function. And this pair is often used. We often use this way that the autocorrelation function Fourier transform is a power spectrum. So if this is a spectral domain, you see that you already taken modulus square to represent the power distribution across S. And if you do not get this directly measured, people have been using autocorrelation functions of the signal and then Fourier transforming it to get the power spectrum. These are additional things. If you take a derivative of the function, you will find it acquires an extra term proportional to the coordinate in the Fourier domain. Okay. I will not go into this except to highlight you can do the convolution. One of the things that you will notice that since it's a product of the Fourier transforms, when you convolve two functions in one domain, the sequence in which you convolve does not matter whether you convolve f with g or g with f. Whereas in the correlation, it matters whether you correlate A with B or B with A. And that, again, as you can see, is only flip of the axis of the relative delay in the autocorrelation function or correlation function, cross correlation function. Autocorrelation is the correlation with itself. Then there is this Rayleigh theorem, which is nothing but it's also known as Parseval's theorem. And this is simply a statement of conservation of energy. There are other variants of it in terms of how the power is computed, cross power, and how that does that translate in the other domain. All right. There are so these are simple examples. For example, the shift theorem. You will find if a nice rectangular box centered at 0 is to be viewed and its Fourier transform, you will find that is a nice sinc function. Whereas if the box was shifted from the origin, you will find that due to shift theorem, you can apply this function times the linear phase gradient. And you will find that because of the linear phase gradient, this contribution, where the sinc function describes the amplitude, will now split into real and imaginary parts in the fashion that is shown here. Now, depending on the amount of shift, you will find this oscillating pattern being faster or slower. If the shift is larger, you will have faster oscillation because the phase is changing more rapidly. And for every 2 pi change of phase, you will have the peaks occurring. All right. There's no change in amplitude. Only the phase has changed. All right. You can also look at, this is what we already talked about, convolution, and in one domain is a product of Fourier transforms in the other domain. And as I said, the order does not matter, and it comes from a simple thing that we understand about multiplication. So they commute. Okay, so the All right, so this is a specific thing which I mentioned about modulus square of the function in one domain, particularly if it's in the spectral domain. We get the often desired description in terms of power spectrum, where we can measure the intensity as a function of frequency, and which has a Fourier relation with autocorrelation, which is what they used to do in early days. Although it's difficult to build finer spectrometers, you can use this relation to get very long span of delays in the autocorrelation function, and which gave you very fine spectral resolution because of this relation between the span in one domain is defining the resolution in the other domain, and vice versa. You can also perform cross correlations, and what you will get is what is called cross spectra. If X happens to be time, and then S happens to be the frequency. This is what we routinely use in measuring similarity between the electromagnetic fields received at the two spatial locations, particularly in the two-element interferometer that we discussed at great length. And this will be a measure of the spatial coherence between for that part of the sky at a given baseline. So here, of course, order matters, and the change of order simply amounts to flip of the axis. In the case of our real brightness distribution, which I already referred to, the visibility will be complex conjugate of the otherwise. All right. This is just highlighting explicitly the linear aspect of these transforms. Any arbitrary linear combination is preserved across the two domains. So if you take one function, scale it by some amount, and add it to another function scaled by a different amount, the Fourier transforms follow that scale precisely in the same combination. So you can, this is what helps in the visualization. For example, imagine that you are wanting to know the Fourier transform of this. You can quickly exploit the linearity and imagine this to be sum of a rectangular function plus a triangular function. A rectangular function has a sinc function response, a triangular function has a sinc square response, and you add the two with the scales that you think and the widths of these functions as you see them. You can quickly get to the answer before having to compute it. Okay. All right. So that's, are there any questions up to this stage?
Sir, are there any direct applications of the cross spectrum in astronomy, let's say?
Yes.
I know that the power spectrum has quite a few applications, but what about the cross spectrum?
Yeah, the cross spectrum is what we measure in the interferometric situation directly to find out the similarity between the two signals.
Okay.
Which might differ, which might have small differences across the spectrum due to a variety of reasons, because of some uncompensated delay, which will show up as a phase gradient in the cross spectrum, and so on and so forth. So cross spectrum is actually nowadays more used than, and it's also used in filtering. If you want to detect a pattern, for example, what people who detected gravitational waves using the templates cross-correlated with the observed signal would have done exactly this. They would have Fourier transformed the two, right, and multiplied one by the complex conjugate of the other.
Okay, sir. Thank you.
When they wanted to find out the delay between the two stations that they measured the gravitational wave signal, they would have done also the same thing. They would have taken one, they would have taken both separately, Fourier transformed, and taken multiply one by the complex conjugate of the other, and then you will find that there is a linear phase gradient across the spectrum, which when translated would give rise to a spiky feature showing the correlation matches at this delay. So accurate determination of delays and so on are done through its Fourier domain and assessing situations there.
And I guess wherever like two or more different instruments are used to like observe the same thing, I guess there also cross correlation.
Any comparison, any
Yeah.
correlation assessment is done through cross spectrum. It can also be done where the spectral axis is not retained, information is combined, but that has its price to pay, because if certain things are changing as a function of frequency for a variety of reasons, you would wash out that effect and may not get a chance to account for it properly. And that might destroy the level of correlation that might actually exist in the.
Right.
So cross spectrum is one of the most commonly used descriptor and tool for a variety of purposes. Autocorrelation function is a special case of it. I mean, the power spectrum is a very special case of it, when both of them are same. Okay, looks like there are no other questions. Okay.
Desh, if you have no other questions, you could probably stop today, no? They have a day.
Yeah, I'm not going to do the second session of the fourth. Basically, I've given them a gist of it. Then I will go, and part of it I have already talked in my earlier session about coherence and so on. So I may not need to repeat that tomorrow. So I'll see what is not yet said and leave that for tomorrow.